And you should be taking notes on your classmate.
We already made a deal.
Oh, really?
They're
We're
paying
photocopying
me.
each other. We're just going to photocopy the notes we have for the board and throw it around.
Well, that's just as long as you revere them as tablets down from the mouth. Okay, so.
I'll photocopy them on golden paper. Analyticity, everybody say that.
No.
Some of us can and some of us can't, okay.
Well, okay, at least I can say similarly.
Barely. Okay, we'll start with a definition. Oops. Ready anything? That's a D. So a complex value function is analytic on an open set D if it has a derivative at every point in D. And so that's what we're building up to, but we need to go back and look at what it means to be to have a derivative. So another definition. Greg, they have a thing here. Does that mean congruent?
Oh, it means equivalent.
Okay.
The modern use would be, I think now computer science has infiltrated mathematics a little bit. That thing is now written as colon equals.
Which? This,
The equivalent thing that you see in the book,
this one right here?
usually most books will now put that as colon equals
Oh, okay.
to mean defines. Yeah.
Okay, so. I write fast. So that's the definition of a derivative for a complex value function. You'll notice that it looks an awful lot like the one that we're familiar to, provided that the limit exists. So far, it's looking kind of the same. There's an example, which is actually in the book, and it's that. They use the definition, plugging it into putting this into the definition there, and using the binomial theorem, they get that, which we might expect. Using the definition, I'm forgetting a piece, so I don't remember what's in the book. They come up with this: the limit exists for all points on the complex plane. So this thing is differentiable everywhere. It's therefore analytic on the complex plane. So this is one that's okay. Let's see.
Because a complex plane is an open set.
An open set.
A big open set.
Yeah, C instead of D. Okay, there are two, let's see, no, I'm not going to do that. You guys can have a photocopy of this. There's a theorem in the book, Theorem 3, that gives rules for differentiation. And if you've got your book there, you can see it. I've looked at other books that expand it a little bit, so I'm going to write it down this way. Oops, if F and G are, let's see, how does it say it? f and g are analytic functions on D, that means that they're differentiable according to that, then we get these properties. Did I write them out? Yes. And this thing is also analytic on the same open set. Similarly,
Should have said it in grade.
Just a little notation thing, since you got me on similarity. If you evaluate the function at z, then you should do it on the right hand. So f plus g prime of z should be f prime of z plus g prime of z.
okay.
And similarly, or you can do that. That saves it.
Saves a little bit, all right. Okay. The fourth one is, oh, yeah, I read it. No, I was this one. It's analytic on D as long as G doesn't equal 0. So if there are any Z values that when you plug it into G and you get 0, then obviously it doesn't work. And the last one, I have to be careful now. Now I want to put in the Z, and I have to maintain the pattern. Okay. And here the restriction is that since f is going to be evaluated based on the function g, then whatever g gets from that z also has to be in the same open set, because if g of z gives something that's not in D, then you can't even evaluate f. So you have to have that. But the point is that all of the rules for differentiation are the same when the function is complex valued. So that's easy. We can just do all these things and just treat z as if it were an x and carry on from there. The problem is that not all complex value functions are differentiable, and certainly not as sort of uniformly as the regular ones that we see all the time.
From memory, the camera doesn't pick up
That's a lot
things.
better, yeah.
If we turn the lights off at the front page. So.
Okay, so the problem is, I should have, oh, that's okay. The problem is that when we're taking a limit with the complex value function, the delta z can approach z naught from infinitely many directions, not just from the left and from the right like we're used to seeing. So it can come in from the left or the right, but it can also come in from the top or the bottom, or it can come in on a spiral, or various other things. So the limit has to be unique, no matter which way it approaches that spot. So, let's see.
So actually, that's an extremely important point. It means that for a complex value function to be differentiable, for a complex value function to be differentiable, it means the answer has to be the same on any of these infinitely many paths, which is a very strong constraint on what functions can be differentiable. And that's going to be the source also of the power of methods, complex methods for functions which are analytic.